think we're good to go then. So welcome everybody. Thanks for joining the session about how we did at NGINX server-side WebAssembly the real hard way. And yeah, it was really painful. Yeah, first of all, I'm your host today, and I'm really proud to be so. What I'm doing is I'm working at engineering for NGINX, being a Docker captain, software and technology lover, and hacker when I'm not doing all of this stuff that's above, which I already mentioned. And before we dive into the experience we had and what the learnings we had, I would like to start with a little timeline. So, back in February of 2023, we had this good idea of, hey, we could add WebAssembly to NGINX Unit. NGINX Unit is our new open source project. I mean, new, it's a couple of years old already, but it's not so well known. It's an universal web application server that can run your code natively in 7 different languages. So adding WebAssembly to this as number 8 was kind of an usual thing, and it was like, it did make sense to us. So yeah, February we said, let's add WebAssembly support to NGINX Unit. Well, then we were working on the release 1.30. We released 1.30 in May. So in the meantime, between like mid-February and beginning of May, I did a lot of research about all the things WebAssembly, as I was a really WebAssembly newbie back in the days. And then after May, we had one engineer working on something like the Wasmtime integration for the runtime, and then we built the first WebAssembly modules. Then we tried to execute those WebAssembly modules on NGINX Unit. Then we saw that this is painful because of something that's called linear memory, so we created an SDK on top of all this. And then we found out that, hey, C is great as NGINX Unit is written in C, but a lot of people would like to use Rust. So we ported our SDK to Rust, and that opened up a whole new area of, hey, that's fine, but then you have to do bindings. And with bindings, we would like to share this Rust SDK with the world, so we need packages and crates.io, and well, with 1 PM, that's me, 2 C engineers, 1 QA engineer, 1 technical writer working on this, the full time was like, well, yeah, this is fine. Like, we basically spent like, you can see, like my wife is saying I lost a couple of hairs, and I think that's due to this thing, because it was a lot of night works and a lot of reading and a lot of investigation of things. And at the end, it turned out it was like this bubble of words and things and different topics that were just mind-blowing. If I started with digging into WebAssembly, it is overwhelming. You get like a million things you've never heard about, or maybe you have heard about, but it's like overwhelming. So what I did next is I've tried to structure this a little bit, and I would like to take you on to this journey, what I did from basically mid-April till 31st of August, where we released that finally. And the first thing I actually did is I Googled, what is WebAssembly? Like, what is this WebAssembly? And on the website, there is a sentence saying WebAssembly, or Wasm, is a binary instruction format for a stack-based virtual machine, and it is designed to be portable, and it can run on the web server, on the client side, or on the server side. And this first sentence was a little bit like, wait a minute, binary instruction format for a stack-based virtual machine? That was like, I think I've heard this somewhere a while ago. And just imagine, I was sitting in my room, and it was in the middle of the night, like dark, almost. I was sitting there and reading this sentence. It's a binary instruction format for a stack-based virtual machine, and I have a huge bookshelf in my office. And there's one book in it. I've not looked at it for not a decade, but for a long time. I looked at it and I said, look, I don't really want to pick this book out of my bookshelf, right? It is there for a reason, and it was a little dusty, so I took this out. And then on the first couple of pages, they told me that what I'm holding in my hand, glad you're using it, is a language that can be compiled into a binary construction format and can run on a virtual machine. If you Google for this virtual machine, it tells you very quickly that it's a stack-based virtual machine. And guess what? I was like, please no, stop. Right? So and I was like laughing very loud in the middle of the night because I'm now starting with something that is the new hype, the hot stuff. And the first thing I learn about this hot stuff is that it's literally like Java. So, just kidding. That was my first impression about WebAssembly. And the next thing I did basically is I've tried to understand what is a stack-based virtual machine. I know what Java is and I know what the JVM is, but I Googled a little bit around and found some great YouTube videos and tutorials about this. So I basically got some stuff from the internet and tried to just copy it and generate it and understand what is this stack-based virtual machine. So a stack-based virtual machine needs, first of all, a set of instruction types. In this case, we have just 3. The WebAssembly stack-based virtual machine had hundreds of them. So it's huge, a lot bigger than what we have here. But the reason why I put that here is because I would like to give you an idea of what is the stack-based virtual machine. So we have a set of instruction types. In this case, 3, push, add, and print. An instruction is basically the what and how you would like to do with something. So it needs this instruction type, and then this is the what, and then how would you do it. So, and the program is here on line 12 to 17 is basically just a list of different instructions in a given order. So first we say we push a number to the stack, then we push another number to the stack, and then we call this add instruction, and then we call a print instruction. So and then we need some VM operations like helper method, glue code to push things to the stack, to pop things from the stack. And the right part here is basically our main program. It reads in the program, and then it checks, okay, what is the instruction? Is it push, or is it add? Is it pop? Is it print? So what is the actual instruction? And if it reads an instruction that's not supported, it just says, hey, this is an invalid instruction. Perfect. So in the nutshell, this is basically what a stack-based virtual machine is doing. So and the most important thing is it just iterates over all the instructions given in that file or in that program and executes it one by one and in sequential order. That's it. That's the stack-based virtual machine. To me, that was very important to understand because everything that comes next is like what can be compiled into WebAssembly. And I read a lot about what languages and what languages can be natively compiled in WebAssembly and what with some boilerplate, polyfills, glue code in the middle. But one thing that was really important was this what format. The WebAssembly insertion text or the WebAssembly text format. And the reason why I'm saying this was important is this helped me better to understand what at the end is this what file, what is the format, and as I already knew what is the stack-based virtual machine and what is this binary instruction format, it was not too crazy what I saw in this file I will show you in a minute. This QR code is a pretty interesting GitHub repository I found during my research. It has a list of basically all the different languages you can compile to WebAssembly. There is C and C++ and Rust and Go at the very beginning, but there are also a lot of other languages with all the polyfills you would like to use. So this is definitely worth checking out and bookmarking in. All right, so the first thing is maybe not the most obvious thing, but if you would like to understand the very basics, for me this what format was the way to go. So the what format is basically a text format that is human readable, and it's these typical S expressions. And what you can see here defines a module for the same kind of program we saw in the C example to add 2 different numbers and print the result. So what we do is we define a function that has 2 params, and in this case we can see it's an integer as an import and an integer as an export, and we name this function add. So then at the end we see this what to Wasm, then we compile basically this what file, this text file, into a WebAssembly binary file. This is what we do here, very simple. So now we know what is a stack-based virtual machine. We have a very, very simple textual format that we can, and this can be compiled to WebAssembly. Great, so now I have a binary file. What's next, right? So that was my next logical thing. So what can I do with it actually? Right, so the next step was basically to find a runtime that can run this file, that can execute what I've just built. And there are a lot of different WebAssembly runtimes. That's why I'm not saying Wasmtime is the best runtime out there. You should all use them. It's just the runtime we picked for NGINX Unit because it has a very well documented C API, and as NGINX Unit is based on C, I needed something I can give to our engineers and say, look, this is the C API, this is Wasmtime, now try to bring them together, to combine them and integrate Wasmtime into our application server. That's why I've chosen Wasmtime to play around. Okay, so then I downloaded Wasmtime, played around with it, executed my absolutely amazing WebAssembly file that adds just 2 numbers. It's literally like a hello world, just a little bit more nerdy. And while looking at the Wasmtime website, I found another thing that was called, at the very bottom it says WASI. Wasmtime supports rich set of APIs interacting with the environment through WASI standard. Dang it, another thing. You remember this big bubble at the very beginning of the session, this word map? That's what I mean. Another thing, WASI standard. What is a WASI standard? I had literally no idea what it is. So the next step was to understand what is actually WASI. All right, so read a lot, WebAssembly system interface, and this was also a very interesting thing because now this was the moment in time where all the things come together and where I finally had at least a basic understanding about what I'm doing. So the WebAssembly system interface is designed to provide standard interfaces to your WebAssembly binary to interact with the outside world. And by interacting with the outside world, I mean you can write C code, you can write Rust code and compile it to WebAssembly. Perfect. So, but how useful would it be if you just have things inside of your program, but you cannot use like POSIX APIs on Linux, or you cannot interact with network, or you cannot interact with like your file system? I mean, that's the most common thing. You have something, and you would like to write it to a file on disk. So, with normal WebAssembly, without WASI, for example, it would be very hard to tell your WebAssembly binary how to access the underlying file system of your host machine. So I read a lot about this. First, that you have to allow Wasmtime to provide access to a given directory on disk to your WebAssembly module. That's one thing, because WebAssembly is secure and sandbox and isolated. So if you would like to break out of this isolation, you have to tell your runtime, your host in this case, hey, please provide access to this given directory. Perfect. And WASI helps to define those interfaces in a standard way that you can use your standard C APIs, your POSIX APIs you all love, like freed and whatnot, and just write them and compile them to WebAssembly. And while you're writing it, you don't even care about the target, the deployment target. So, at NGINX, we do a lot of C, and we finally do some Rust as well. If you would like to compile from C to WebAssembly, there is, for WASI, something called the WASI SDK. You can download the WASI SDK and use it in Clang for your compiler. And while you're compiling your C file, you define a special compilation target and say, hey, please, Clang, the target is WebAssembly. It will be Wasm. So what Clang will then do, it will look at the WASI SDK and translate those POSIX APIs you have used in your code into something that is actually WebAssembly compatible or compliant. For Rust, the world is a little bit different. For Rust, it's easier because Rust adds a compilation target kind of natively. In Rust, everything feels a little bit more natively than in C, as long as you have not to deal with raw pointers, and I will come to this in a minute. So for Rust, you can add a compilation target that's called Wasm32 WASI. And we have a demo. Later in this session, I will show you how you can simply add this compilation target to your ecosystem. It's a one-liner. That's it. Very simple. All right. So this was basically the kind of information I collected over my journey. And now I would like to give you a better overview about where we implemented this WebAssembly runtime. Because I was talking about NGINX Unit for a long time, and now I will give you a little system overview, an architectural overview about what NGINX Unit is. As already mentioned, it is kind of a universal web app server, and we support natively 7 and now 8 different languages. You can share static files. You can host multiple applications next to each other. You can configure your listeners with TLS and manage your certificates. And one thing that is super important in this diagram is what we see here, and that is different what we saw previously with Wasmtime, or just run this WebAssembly module in Wasmtime, is in this diagram, it's the first time that we see an interface to the outside world. And I'm not talking about WASI. I'm talking about an interface that your users, or you as a client, can actually use. And here it's HTTP. So, and this was another challenge, because obviously you can compile everything to WebAssembly. That's fine, right? But it's not super helpful if you can just run it and execute it on a runtime on a server, but you're not providing any interface to a client that can actually then make use of it. So in this case, for NGINX Unit, it was obviously that we would like to use HTTP for that, because we already have an HTTP router inside of our unit application server, so it sounded like a very good idea just to use HTTP. Okay, so we defined this interface, HTTP, and all we have to do, in very, very big quotes, look at my hairs, very big quotes, all we have to do is take this HTTP request, simple, do something with it, like put bytes, basically, raw bytes, right, and send it to the WebAssembly module. Then the WebAssembly module can do magic stuff with it and just send the response as bytes back. That sounds pretty simple and very straightforward, so that should really work out of the box. Yeah, that's what we thought, at least. Right, so, and I made a very nice picture, and actually, you now may scream or not, I mean, Matt maybe, because in this picture there's a fundamental problem, and I've not updated the slide because of a reason. Because at this time, I didn't understand it well enough how this linear memory works. So I created this slide and sent it to our engineer and said, look, lovely engineer, I think that we have this unit derouter process that will take the HTTP data, and then we have this already implementation of shared memory, so we can send this data to the application process, perfect. Then we can take the raw bytes, and then we can initialize linear memory and send it to the Wasm module, and everything will be fine. Good. And I sent this diagram. The problem with this diagram is this little blue box you can see here is at the very, very wrong position because the linear memory is part of the Wasm module, of this gray box that's on the very bottom of the thing. This Wasm module takes care of its own linear memory. It's not in the runtime. Wasmtime is like, you initialize the linear memory. It's like opening up the bucket where you put all the raw bytes in it. You manage this from inside of your WebAssembly module, not from the host, not from your runtime. And I had this wrong assumption for far a long time, and that was very hard, because if you have this in mind, that the runtime, like your Wasmtime, is managing the linear memory for the module, you will not be very successful implementing it, trust me. This will not work out well. So this is why this is wrong, and this blue box should be a little bit further down in this picture, because the Wasm module itself initialized linear memory. So what is linear memory? And what is linear memory? There's a great blog post from Fermion's very own Radu, who made this, and it's an amazing resource because it explains in a nice way what linear memory is. So, WebAssembly, if we consider this web file from a couple of minutes ago, we saw that we can have imports and exports of functions. Like we can send data in and we can get data as results back. Right. But one thing with WebAssembly is that we can, based on this stack-based virtual machine layout, we cannot handle non-trivial data types. What is a non-trivial data type? Anything that's not, in this case, an integer or a float number is non-trivial. For WebAssembly, a string, no way. It's an array of characters, no way. Non-trivial. Bytes, non-trivial. If you would like to send an HTTP context, like a whole HTTP request, including the metadata, maybe a request body, I think we all agree this is far beyond a trivial data type, right? This is different but non-trivial. Okay. So we looked into the documentation again in Radu's blog post and says, okay, if you would like to share those non-trivial data with your WebAssembly module, you have to do something like linear memory. Okay, linear memory, sounds good. And linear memory is kind of a bucket that is managed by the WebAssembly module itself to receive non-trivial data, like in raw bytes. And if the WebAssembly module is doing something with those data, obviously, it will put the result back into this bucket and tells the host machine, hey, I've computed your result, and it's here in my bucket, starting at this position from my linear memory, and it has this size. Feel free to take it, but please tell me when you're done with it. And that's what I've tried to like illustrate in this little diagram. As said, it's in a nutshell on a very high level. It's technically not 100% correct, but it should give you a little bit of an idea how that works. So from the host, you request in terms of, like, think of the HTTP request. We receive the HTTP request, and we would like to send it to the WebAssembly module. So what we did, basically, is take the HTTP request and get its size. So how big is this HTTP request, including request body and headers and URI and arguments and cookies and whatnot. So then we ask from the host, we ask the WebAssembly module, hey, dear WebAssembly module, I would like to send an HTTP request with n bytes. Okay, the WebAssembly module then says, fine, perfect, that's what I'm here for. Please take this pointer, right? Take it, and I've created a box for you, and please put your raw data in it. Just put it in. Okay, so then you do it. Then you put the raw data from this HTTP request in this bucket opened by the WebAssembly module and call the actual function. You did it, and then you call this HTTP request handler and say, okay, now WebAssembly module, do something with it. Fine. The WebAssembly module reads the raw bytes from memory, puts it in a structure, then you can do stuff with it, whatever, then you have a response. Okay, so what the WebAssembly module is doing then is it puts this whole response again in this bucket at another position, puts it in, and sends the response to this HTTP request handler is basically, hey, I put the response at this pointer, and it's this big. It has this length. So on the host side, you can then go in the linear memory from the module, read n bytes from this position, put it in a structure, you have the response, send it back to the client. All is happy. Okay. This is in a nutshell. This sounds really easy. And this is like another illustration how that works. Like we have the post request, it sends data, then we have the byte stream, goes into WebAssembly. From WebAssembly, we have another byte stream, goes back. Then you can see the result in your browser or in curl or whatever. So, but I promise that it was like a week or two, if not longer, to deal with linear memory. Because on one side, we have unit, which is written in pure C. On the other side, the WebAssembly module is written in Rust. And that's what I said. If you have ever tried, Rust is straightforward, I agree. But if you have ever tried to deal with raw pointers in Rust, because they come from C, and then you have to deal with raw pointers in Rust, because you cannot use a vector, because then unit is not able to read those vector information from Rust, because it has some metadata that's part of this bytes in linear memory. This is painful. This is really painful. And if you try to debug this, this is even more painful. And yeah, we did this a couple of weeks, and I I remember we had a chat with Fermion and with Matt and a couple of people from Fermion, and I said, look, this is painful. Yes, it is. But you have to do this exercise to understand actually how this whole thing works, how this linear memory works. All right, and I will send you a link to the GitHub repository, so you have this then in a much bigger format. So what we see here is basically the code we created, or the SDK we have created, to write actual Rust code and compile this to WebAssembly. And this was a long process, because we tried to deal with linear memory, and that is painful. If you do this, if we would let a user do this by themselves, this would be painful. You cannot release something and say, hey, please deal with linear memory. It's easy. You have a raw pointer here and another raw pointer there, and then put raw bytes in it, and then you're all good. No, this will not work. So we have created an SDK. And as said, we in NGINX, we use a lot of C code everywhere, not so much of Rust. So this was actually one of the first things where we dealt and worked with Rust. So the whole ecosystem was also new, because we shipped a package, because we wanted that a user can simply do something like cargo add unit Wasm, and it just works. And if you have an example code from us, it just works. You don't have to deal with a lot of stuff by yourself. And I thought it would be a lot easier to publish a crate, or basically create a package for Rust that has like bindings to the C code, because we had this unit Wasm SDK written in C, which is not helpful because we need it in Rust. So we had bindings, and we generated those bindings, and from those bindings we had done those FFIs, foreign function interfaces. We had to implement those, and then you package everything up, and then you can publish a crate. Yeah, well, it worked on my machine. That's the sentence, because I forgot that this crate cargo stuff will be compiled on every machine. And if you have some data, some path directory definitions to, hey, your .a.o files are basically sitting here, this cargo build works perfectly on your machine. No problem, because the A and O files are exactly here. If you send this to your colleague, coworker, or even more problematic, to a real user that just downloads the crate, will not work, never. So it sounds stupid right now, I'm staying here and saying this, but this was something I did not know back like in May. Was like, okay, that was unexpected. Because then I learned a lot about cargo and how that works, and cargo build and cargo publish, and finally we made it. We have two crates on crates.io. It's unit Wasm and unit Wasm sys as a dependency. Following best practices, the unit Wasm sys crate is just the FFI interface, like the raw C bindings, and the unit Wasm has the unit Wasm sys as a dependency. And trust me, if you will read anything about FFIs, this is the first thing you see: create a sys crate and then implement against the sys crate. That's what we did. And yeah, we have two crates out there. Good. So far, so good. So we have now a WebAssembly runtime on top of Unit. Good. We have a C SDK that was ported successfully to Rust. Also good. We have some crates that can be consumed by the user. Very good. It works. Also good. And now we have to write some documentation and make it more clear. And I would like to give you now, the last like 16 minutes, a quick demo how that actually works, basically. And it's all live. I mean, you can download Unit right now and test it and play around with it. It's live since August 31st. So yeah, I just would like to give you a quick demo how that works. All right, so in here, we already, oh, can you actually see this? No, I have to escape the presentation first. Now you can see it. Yep, okay. So as said, we have this little beauty. Is it big enough? I think so. So here. This is the very first thing you have to do. Rust up target at wasm32 WASI. This adds the compilation target of your Rust code, and that you actually can use WebAssembly as a target. If you compile it with Rust or cargo build, then you can use this target. It's already installed on my machine, so we don't have to do that. Okay, perfect. So that is number one. Number two is we can start with cargo init, for example, here, and say, okay, this is a library. Reason why I'm saying it so clearly is it is a library. You know what? I have tried at least 2 days creating this demo without a lib, and it was not working because it's not a library. So it is obvious that you need a library. For me, in April, it was not obvious. So I lost 2 days just because missing -- lib. So make sure if you do this, cargo init -- lib, whatever you want to do. So then it will generate a cargo project for you. Then you can do cargo add unit Wasm to have our SDK. And before you compile it, make sure that you put inside of your cargo.toml file, you define that this is a CDY lib. Per default, it's not in it. You should put it in lib, create type, CDI lib. Good. And here we see the dependency. This is a simple cargo add. So in source, there's then a lib.rs file. And here we see this is our Rust SDK. And basically what we have here, we have a couple of functions. That is some boilerplate for the initialization of the linear memory. And then, this is not a hello world example, by the way. This is an echo server that prints out some debug data. That's why it's a little bit bigger. Here, we export the functions from the Wasm module to make them available to the host. Here we see, we write a string, write string, 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 string. Here we see some response data. And then at the very end, init response headers, we set the headers to explain. We send the headers, and at the very end, we do the response end, and we turn to 0. We have this full demo on GitHub. You can simply download it and clone it. And then if everything is ready, you can simply do cargo builds and then define the target Wasm32 WASI. It's already done because I don't trust the demo gods, right? So I've already built it. If you do this the first time, it will download a couple of dependencies from our unit Wasm and unit Wasm syscrates. And after all, it should finally compile your WebAssembly module. And this sits normally inside of the target. And there's Wasm32 WASI as the target. Then debug, because it's non-production. If you would add the packaging command, then you would not have this debug information. But it's useful because you can, even if you're running it on NGINX Unit, you can enable the trace output so you can see what the Rust code is actually doing. So here we see the Wasm on unit Wasm module. So this is actually our Wasm binary. Great. So now we have a Wasm binary, and the next step is actually put this in a container. As we are on DockerCon, we should definitely put it in a container. Good. So we have a base image, unit Wasm, that had everything. That this comes with all we need to make Wasm work. So then we copy our WebAssembly module inside the container, and basically we add the cmd command, which spins up NGINX Unit on port 9000. And this port 9000 is just the configuration API so that we can send dynamically updates to the application server. You may not use this in production, but for demos, it's actually very good. All right. So then we can do docker build, and then docker run. And another thing I would like to show you is the config for the WebAssembly module. So we open up this interface to the outside world on port 80. We tell unit it should send all incoming requests to our WebAssembly application. The type is Wasm. The module we want to load is this. And then at the moment, we have to define like the bindings between the Wasmtime host implementation. Our module is to tell NGINX Unit what's your request handler, what is the malloc handler, like what can I use actually to ask the WebAssembly module for more linear memory. That's here. The free handler is the other way around. If I'm done with processing, I can tell the WebAssembly module to free the linear memory. And the module init handler is on application startup to initialize the initial linear memory with 4096 bytes. And the end handler is on shutdown. When we shut down NGINX Unit, it calls the end handler of the WebAssembly module. So this is basically the configuration for NGINX Unit. And then you can put everything together. And then you have a container. Let me see. Just would like to use one, because then we don't have to reconfigure it. So now we have the Wasm demo. And here you can see it has the Wasm module, and we expose it on port 8888 to the host, and port 9000 was the configuration API. When we click on this, that's not what I wanted to see. Then let me do actually another, let me do this real quick. So we have the config, so we have the Docker build. Let me build it. Perfect. And then we run the Wasm demo. So make it light. So now it's actually running. And now we have to configure it real quick. You can put this in the container per default as well. So we check it again, okay, works. And then we send it to the configuration. It says reconfiguration done. And now that's the welcome page on WebAssembly. A neat thing you saw, we don't have to reload NGINX Unit, we don't have to restart anything. It's literally live and hot reload on configuration changes. And what we see here is basically the Rust code we just compiled into WebAssembly with this echo server saying, okay, we received this GET request and we have these request headers, and it should actually do something, should do the same thing on curl as well. When we do, what is it, 8888. Says the same thing. And let's see, when we put a header in here and say x test, this is DockerCon, it adds a header here at the end. So it's basically taking the HTTP request and puts it from linear memory, puts it back in the response, so we can actually see this. So what are the next steps, basically? The next steps are that this was a great example, but we have not made use of WIT or WIT bindings. This is another thing from this big bubble at the beginning. WIT files are basically interface types or WebAssembly interface in definitions. You can build C and Rust code against it, that we don't have to basically generate the structures by ourselves. So this is definitely the next step. Then we would like to add more features from WebAssembly to our implementation so that we are compatible with WASI HTTP or the WASI Cloud Core features. And of course, investigating more time into the Wasm or WebAssembly component model, which is, I think, an amazing thing. But if we start digging into the component model thing, we would not be out of this room by 11 or something. So we're not doing this. Yeah, at the very end, yeah, it's good that Matt is here, because I would just like to give a special thanks to Fermion. That was always good talking to you, and all the blog posts, especially the linear memory thing from Radu was super helpful, and all the great sessions on Slack where we ask questions, and of course Docker for the great community. I had a couple of chats with Ralph as well from Microsoft, which is from the Bytecode Alliance, and I mean it's just great and amazing to see that we are working for NGINX, of course, but we are not alone. This is a community-driven thing, and we all work here in the open source world, and it's just great to see that it's Fermion is supporting, and Docker is supporting, and NGINX now is working heavily on the WebAssembly thing, and it just feels great to be part of a bigger thing, of a bigger community and bigger family. So that's why a very, very big thank you. And we have a panel discussion actually coming up with Matt and Nigel in the breakout room 2, starting at 5 after 4, so 16:05 something. So if you would like to learn more about WebAssembly or hear what's the maybe current state about a component model and what we think about it, you're absolutely invited to our panel discussion in breakout room number 2. And now I am open for questions, if there are any. No questions, always good. Perfect, then thank you very much for listening, and if you have questions, let me know. Thank you.